Hello everyone. Today we will start with the session 2 of the 16th group, right? The halides and the oxides we will be covering in today's session. Halides and oxides of 16th group elements. We will be starting in a while. You can just drop down your names for attendance purpose. Okay, good. So we'll start with the session now. First, we will deal with the halides of the 16th group elements. We'll get a review. What were the 16th group elements? Oxygen, sulfur, selenium, tellurium and polonium. These were the 16th group elements basically, right? Now, coming on to the basic formula or the empirical formula of halides, if you see that types of halides that can be formed here are MX6, where X is the halogen basically and M is our element. M is the 16th group element. The type of oxides that are being type of halides that are being formed here are MX6 such as SF6, SEF6, TEF6, right, or MX4, SF4, SLCl4, SEF4, SECl4, or MX2 if you consider TeCl2, TeBr2, TeI2. For polonium if you consider PoCl2, PoBr2. There also are the type of halides such as M2X2, such as O2F2 we have discussed in the previous session, right, in which the oxygen was having basically what? The +1 charge, right? And here M2X if you see ClO2, BrO2 and other oxides are also mentioned here, right, such as S2F4, S2F10, Cl2O6, Cl2O7. So all these elements form a number of halides and the halides of oxygen are not very stable. This is important. Halides of oxygens are not stable and the stability of the halides decreases from fluorine to iodine. For example, if you consider, let us say SF6, SCl6, SBr6, Si6 and so on. So the stability of SF6 will be greater than that of the chloride, bromide and iodide one. Now we'll be dealing first with the hexahalides, that is MX6, right? So among hexahalides, if you see, hexafluorides are the only stable halides, right? Let us know why. Because here if you see the coordination number of sulfur is coming out to be what? Basically 6, right? That means 6 atoms are surrounding the central atom. Now if you take chlorine, bromine, iodine if you take, let us say, so what will happen here that chlorine, bromine and iodine are bigger elements, right? They are bigger in size. So what will happen? That coordination number 6 will be not fitted to them, right? As they are bigger in size, so overcrowding will take place and therefore the stability is less. Okay. Now if you see here, fluorine brings out the maximum valency of 6 with sulfur, selenium and tellurium. So if you see SF6, the oxidation number of sulfur is +6. If you see selenium, it is +6. If you see TeF6, it is also +6. So here if you see that the hexafluorides are covalent. Why? Because according to the Fajan's rule, greater the polarizing power of the cation, or you can say the smaller the size of the cation and greater the size of the anion, more is the covalent factor, right? So here if you see that it is exhibiting +6 oxidation state, that means the cation that is being formed, S6 plus, Se6 plus, Te6 plus is very small in size, and as the cation is small in size, therefore it will possess a more covalent character, right? They have octahedral structure. This is the octahedral structure that is shown by basically SF6. Now, how do they form the octahedral structure? Basically, we have discussed in the previous class that how it is giving the sp3d2 hybridization, right? If you consider the ground state of sulfur, what is the ground state of sulfur? Basically 3s2 3p4. Now Write down the excited state. Basically, the S1 also gets excited to the D and the P1 also gets excited to the D. Now, here 6 electrons of fluorine can be accommodated, right, giving a sp3 to sp3d2 hybridization, octahedral geometry. Okay. Now, next question is, why hexahalides for chlorine, bromine, iodine are not observed? Comment down and let me know why hexahalides of chlorine, bromine and iodine are not observed. That means SCl6, SBr6, Si6, why they are not observed? Anyone with the answer? Anyone with the answer for this particular question? I have explained this just now only in the previous slide. Okay, but why MF6 are only stable? Why Cl6 is not stable or Br6 is not stable, I6 is not stable? You are correct that MF6 are only stable, but why Cl6, Br6 and I6 are not stable? Anyone? So if you see here, basically what is the structure of MX6? M, octahedral structure, right? And chlorine, bromine, iodine atoms are so big that there occurs a overcrowding basically. Fluorine atoms are small in size, so they can have a octahedral geometry, but chlorine, if you see, they result into overcrowding, Cl, Br and I6, and therefore the hexahalides for chlorine, bromine and iodine are not observed. Okay. Yeah. Okay, next we will move on to why among hexahalides only TeF6 undergo hydrolysis? Why among hexahalides only tellurium hexafluoride undergoes hydrolysis? Anyone with the answer? See here, for hydrolysis, if you see, the first stage is to permit the larger coordination number, right? So if you see here TeF6, let us say, as Te is greater in size, right? Tellurium is greater in size than that of oxygen, sulfur, selenium. Why? Because down the group size increases, right? So it enables the water molecules to coordinate more efficiently because of its bigger size, and therefore it is the only hexahalide that undergoes hydrolysis. And the product of hydrolysis, you also have to remember, TeF6 plus water will give you basically HF and H6TeO6, or you can write it as basically OH, 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 OH and OH. Okay. Moving on next, halides, that is tetrahalides we will be talking about, right? We have seen that hexahalides are having a octahedral structure. Now tetrahalides, if you see here, see, sulfur, if you see, let us say, right, it is having how many, or let us take a general element, let us say M, which is of 16th group, right? How many electrons are present in the outermost shell? That is 6 electrons. 1, 2, 3, 4, 5, 6. Now tetrahalide, if you see, one bond will be formed with X, 1x, 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 and one will be the lone pair. So 1, 2, 3, 4, 5. That means which geometry is possible? trigonal bipyramidal geometry is possible in which there is one lone pair, right? So if you place lone pair according to the Bend's rule at the equatorial position, you will get a seesaw geometry. Seesaw geometry, right? Can you see this as seesaw, right? So this is the structure of basically tellurium Cl4 with one lone pair and 4 halogens. Now tetrahalides, if you see, they possess Lewis acid character. That means what? They tend to accept electrons. So SF4 on reaction with F2 will give you SF6. Here if you see the oxidation state of sulfur, it is +4, and here if you see the oxidation state of sulfur is +6, right? In SF4 it is +4 and SF6 it is +6. Now moving on to tetrahalides are very sensitive to water. So SF4 on hydrolysis will give you SO2 plus HF. Third point is very important, that is they act as fluorinating agent, right? Here if you see that BCl3 if you take and you treat it with tetrahalide basically of sulfur, it will give you BF3, that means it has fluorinated boron basically, right? Here also if you see that I2O5 on reacting with SF4, what happens here is that SF4 fluorinates iodine forming IF5. So IF5 is basically involving 2 halogens. It is also known as interhalogen compound that we will study in the 17th group basically. Interhalogen compounds, where there is a compound which is formed by 2 halogens. Okay. Next we move on to the dihalides basically. So for dihalides if you see, the examples are SCl2, OF2, TeBr2, and they are sp3 hybridized. So here if you consider M, how many electrons are present? 1, 2, 3, 4, 5, 6, where M is the 16th group element. 16th group element. Now if you consider 2 halogens, right? So X here and X here. So one lone pair will be here and one lone pair will be here. So how many? 1, 2, 3, 4. That means sp3 hybridization and tetrahedral structure with 2 lone pairs. Okay. So here the ideal angle is not obtained as that of tetrahedral. Why? Due to lone pair repulsion and lone pair bond pair repulsions. So you can see the variation. SCl2 is having 104 degree, OF2 is having 101.5 degree, and TeBr2 is having 98 degree, right? So as we have already done that, bond angle is directly proportional to the electronegativity of central atom. So if we see here that electronegativity decreases down the group, right? Electronegativity decreases down the group. So bond angle will also decrease down the group. So here if you see tellurium, it is having lowest electronegativity, so the angle is also less, the bond angle is also less. This you can remember, that bond angle is directly proportional to electronegativity of central atom and inversely proportional to electronegativity of side atom. Okay. Now I'll write this also, that bond angle is inversely proportional to electronegativity of side atom. Okay. Now coming on to SCl2. So in dihalides, SCl2 is very important, right? It readily adds across the double bond in alkenes. This you will also do in organic chemistry basically, right? So this particular gas, which is what SCl2 is doing, basically it is adding to CH2 double bond CH2, that is an alkene or ethene. So it leads to the formation of disulfide or mustard gas. What is the structure? S, CH2, CH2, Cl, and this will be CH2, CH2, Cl. So this is known as basically what? The mustard gas. Okay. Moving on to next, dimeric monohalides. So if you see that monohalides basically occurs as dimer, right? So it will be S2F2, S2Cl2, S2Br2, Se2Cl2 and Se2Br2. This structure is very important, that is of S2Cl2. If you see, it is a open book like of structure as that of peroxide that we have seen, right? Peroxide is also having somewhat like this structure, open book structure, which is known as. So S2Cl2 is also having a similar structure. On hydrolysis, if you see, dimeric halides will produce HCl plus SO2 plus S, and they also undergo disproportionation. What is disproportionation? Basically, the same species is getting reduced and the same species is getting oxidized. So here if you see, it is in +1 oxidation state. Here if you see, it is in +4, and here it is in 0 oxidation state. So here reduction is taking place and here oxidation is taking place as that of selenium. So therefore it is a disproportionation reaction. Next we move on to oxides. So we are done with the halides. Now we will be doing with the oxides basically, right? This group elements forms a number of oxide basically, right? So if you say monooxide are formed, dioxide are formed, trioxide are formed. So for selenium, monooxide is not formed, right? Basically important here is SO2, SeO2, SO3 and SeO3. These are the important compounds that you need to study here. SO2, SeO2. SeO2 is basically what? A oxidizing agent that you will learn in organic chemistry. Basically, it inserts double bond O, right? SO2, SO3 are gases. We have already done in the contact process. SO2 plus half O2 is giving you SO3, where the catalyst was V2O5, right? So these four compounds are important from the examination point of view. You can just have a look at the reactions of these compounds only, right? Now, all elements form dioxide, sulfur also, selenium also, tellurium also, polonium also, right? So if you see, SO2 is a gas, SeO2 is a volatile solid, and TeO2 and PeO2, if you see, they are non-volatile crystalline solids, right? Ozone, if you consider basically O3, that can be written as OO2 basically, right? So it is an oxide of oxygen only. Next, moving on, SO2, if you know, it is a sp2 hybridized and a V-shaped compound, right? So here if you see 1, 2, 3, 4, 5, 6, and oxygen has the tendency to form double bonds basically. So one double bond here, one double bond here, and one will be the lone pair. So sp2 hybridization 1, 2, 3, where one lone pair is there. So it is having a basically a bent shape or a V shape, right? SeO2 structure, if you consider, it is a infinite chain structure. Here if you see, Se, one oxygen here, one oxygen here. Again Se, one oxygen has been done, one oxygen here, then one oxygen. So it exists as a linear chain. Okay, SeO2 exists as a linear, planar, non-planar, infinite chain. Now this is very important, that the chain is non-planar, right? It is not planar. All the atoms are not lying in one plane, they are non-planar. Now considering the MO3, that is the trioxide basically, the best, that is known as SO3, right? So in solid state it exists as a cyclic trimer, right, or as a linear chain cross. And selenium trioxide, if you see, it is a cyclic tetramer. Tetramer means what basically? See, dimer means 2 units joined, trimer means 3 units joined, tetramer means 4 units joined, right? So we will see these structures. Here if you see, SO3 is a gas which is sp2 hybridized and planar in nature, right? If you consider SO3 in solid form, see here trimer is there, 3 units, 1 unit, 2 unit, 3 unit, right? And in beta and gamma form, it is present in the form of a linear chain basically, linear chain. So SO3 is important from the examination point of view. Next, we move on to, okay, you can write this stuff, then we will move on to the next slide. Now see here, how do we classify basically the oxides, right? What are oxides? The binary compounds of oxygen. For example, you say some form lithium oxide if you see Li2O, or sodium oxide if you see Na2O, or any oxide Al2O3 you see, right? Or many elements forms oxides, right? So oxide can be of metals also and can be of non-metals also, and generally we see that oxides of metals are basically what in basic nature, right? They are having a basic nature, while oxides of non-metals if you see, they are having somewhat acidic nature. And there are also neutral oxide that we discussed in the nitrogen family, right? So based on their oxygen content, right, the classification can be done from two types basically, right? First on their chemical behavior, and second on their oxygen content. So oxygen content, if you see, there are normal oxides, right, in which O2 is present. Polyoxides, if you see, it is O2 2 minus, or superoxide if you see, right? So these are basically the polyoxides. Now if you consider on the chemical behavior, they can be acidic, basic, amphoteric and neutral. Acidic, you know, generally all non-metals oxide. Basic, if you know, metal oxides. Amphoteric, which can act as base also, and which can act as acid also, right? And neutral oxides we have studied in the 15th group. Now because they neither behave as acid and they neither behave as base. Now considering to normal oxides, so if you see H2O, MgO, Al2O3, right, which you form by this formula basically, hydrogen you give +1 and this you give -2, this will be what? H2O. Then for magnesium oxide you will do +2, -2, MgO. Aluminium oxide if you see, Al2O3, aluminium +3 and O2-. Polyoxides, if you see, they have more oxygen content. For example, you say the peroxide ion, that is the O2 2-. Now from here if you see, the one thing that is very much important is that O2 2-, peroxide, O2-, O2-. These molecular orbital diagrams you have to draw. Find out their bond orders. Find out their bond orders. This is your homework. Find out their bond orders. Find out the paramagnetic or the diamagnetic character of each of these, right? So considering the peroxide, basically when oxygen is present in the 2- form, O2 2- form, it is known as the peroxide, somewhat like this. OO linkage is there and minus here, right? So if you consider basically here barium peroxide, if you treat it with acid, it will lead to the formation of peroxide. Here if you take BeO2 in the presence of conc H2SO4, it will give you H2O plus O2, right? So if you treat it with dilute H2SO4, it will give you peroxide itself, that is H2O2, and if you treat it with conc H2SO4, it will give you H2O plus O2. Superoxides, that is O2-, right? So superoxide on reaction with water, they give peroxide plus oxygen. Dioxides, if you see, so MnO2, PbO2, these are the dioxides. So dioxides, if you treat it with conc HCl, they will give you water. Similarly, if you treat it with conc H2SO4, it will also give you water. Okay, so these products you have to remember. First was that peroxide on reaction with dilute H2SO4 gives peroxide, right? Metal peroxides, basically if you treat it with dilute H2SO4, they will give you peroxide. If you treat it with conc H2SO4, they will give you water plus oxygen. Superoxides, if you see, they will yield peroxide plus oxygen. Dioxides, if you see, they will yield water. Okay. Suboxides, now this is very important. So they contain lower percentage of oxygen. These examples you have to basically remember, and the structure of C3O2 is very important, carbon suboxide. The structure is very important. C3O2 is a carbon suboxide and N2O is also a carbon suboxide because it is containing a lower percentage of oxygen. Here if you see that on 2 nitrogen 1 oxygen is present, or here if you see that on 3 carbon 2 oxygen is present, right? While in the general oxide, if you see NO2, 1 nitrogen is having 2 oxygen, or CO2 if you see 1 carbon is having 2 oxygen, right? So accordingly 3 carbon should be having 6 oxygen, but here the oxygen content is less, so they are known as suboxides. You can remember it that way. Mixed oxides, if you see Pb3O4, so it is a mixed oxide of PbO2 plus PbO. Fe3O4, if you see, it is a mixed oxide of FeO plus Fe2O3. Right, so these are known as mixed oxides, which are formed by basically two simple oxides. Two simple oxides combine to form mixed oxides. The example you have to remember, Pb3O4 and Fe3O4 are an example of mixed oxide. Okay. Now, answer this particular question. Which one of the following compound is a peroxide? Answer this. Which one of the following compound is a peroxide? Amongst A, B, C and D, which one is a peroxide? Anyone with the answer? Okay, Sham is saying B. Anyone else? Anyone else with the answer? Yeah, Sham, you are correct with your answer that B is a peroxide. We have discussed this earlier also, right? So, this will be basically what, if you see, barium 2 plus, right? So, this will give a charge on O2 as O2 2 minus. So, this is a peroxide ion. This is how you can identify peroxide. If you see here, potassium will have plus 1 charge, so O2 will have minus 1 charge, right? So, this is basically what? A superoxide. So, the answer is B. Good. Now, oxides classification based on the chemical nature. That means acidic oxides, basic oxides, amphoteric oxides, or neutral oxides. So, what are acidic oxides? Oxides of non-metals. We have already done that non-metals generally form acidic oxides. So, oxides of non-metals which give acids when dissolved in water are called acidic oxides, right? So, why basically the non-metal oxides are called acidic oxide? Because when they dissolve in water, they give acidic, they have basically acidic nature, or they give acids, right? So, CO2 plus H2O, if you see, it gives you H2CO3, which is a carbonic acid. Similarly, for NO2, P2O5, SO2, SO3, Cl2O7, these all are acidic oxides because on dissolution with water, they give acids. So, one will give you what? H2SO4, one will give you HClO4, one will give you H3PO4. So, these are what? Basically the acids, right? The metallic oxides of high oxidation state. Now see here, we already know that oxides of non-metals are acidic in nature. Even the metallic oxides of high oxidation state, for example, here if you see manganese in +7, vanadium in +5, chromium in +6. Why are they behaving as acidic oxides? Because Greater the covalent character, more is the acidic nature. Covalent character is directly proportional to basically acidic nature, right? So here if you see manganese +7, +5, +6, if you see vanadium and chromium, they are having high oxidation state, and according to the Fajan's rule, what is stated that smaller the size of the cation, more is the covalent character. So here if you see manganese +7, it is the highest oxidation state that is exhibited by manganese, or for chromium the highest oxidation state is +6, or for vanadium the highest oxidation state is +5, right? So they are present in the maximum oxidation state, and if they are present in the maximum oxidation state, the size of the cation is very much smaller, and according to the Fajan's rule, they will have a greater covalent character, and we know that greater the covalent character, greater is the acidic character, right? So therefore metallic oxide of high oxidation state also behave as acidic oxide, acidic oxides. Now next we move on to basic oxides, right? So basic oxides can be ionic in nature also and covalent in nature also, right? So oxides of alkali and alkaline earth metals, basically what? Group 1 metals and group 2 metals, if you say, oxides of them are ionic in nature and also are in basic in nature. Why? Because they produce base on treatment with water, right? For example, like Na2O with water, it is producing NaOH, which is a base. So the oxide is basically basic in nature. Covalent oxides, if you see, oxides of transition metals, if you take, are covalent in nature. For example, copper oxide, iron oxide, they are covalent in nature. They are basic also, but they are covalent in nature. While here if you take ionic oxides of alkali and alkaline earth metal, that is group 1 and group 2, they are ionic in nature, right? Now this is very important. They are insoluble in water. Water we know is a polar solvent, right? Is a polar solvent, and as we know that like dissolves like, so here if you see that ionic compounds readily dissolves in water to a great extent, while covalent does not dissolve as much of ionic compounds, right? So covalent oxide, if you see, they are insoluble in water, copper oxide and iron oxide, while ionic oxides, if you will see, they are basically soluble in water, or they dissolve in water. Next, coming on to the amphoteric oxides. So the oxides which can act both as acid also and as alkali also, they are known as amphoteric oxide. For example, zinc oxide. Now this is very important. It is particularly asked in a question that which of the following oxides are amphoteric in nature, right? This question has occurred so many times in JEE also and in NEET also. So zinc oxide, Al2O3, tin oxide, they all are amphoteric in nature, right? So here if you see that zinc oxide, when it reacts with base, it will act as an acid here, right, producing Na2ZnO2. Now here if you see, it is reacting with acid also, so now it will behave as a base and form salt plus water. This is basically a neutralization reaction only, kind of a neutralization reaction, that acid plus base will give you salt plus water. So in one case the zinc oxide was acting as acid, and in one case it was acting as a base. Here also if you see Al2O3, when it reacts with acid, it will act as a base, leading to the formation of a complex AlH2O6 3 positive. While if you treat it with a base, it will act as an acid, leading to the formation of AlOH6. Now it will be 3 minus. Okay. Neutral oxides NO, N2O, CO, H2O, they do not combine either with acid or with a base. So you have to remember that these oxides are neutral oxides, NO, N2O, CO and H2O. These examples you can note it down. Next, we will move on to the question, which of the following oxides react with both HCl and NaOH? So, which of the following will react with both acid also and a base also? Anyone with the answer? Anyone with the answer for this particular question? Which one of them is an amphoteric oxide? Calcium oxide, zinc oxide, N2O5 or CO2? Which will react both with acid also and with the base also. Okay, Shivranjani Sham is saying B. Yes, you are very much correct with your answer. That zinc oxide, because it is amphoteric, it will react with HCl also and it will react with NaOH also. Good. Now we will study about dioxygen. What is dioxygen? Basically O2, right? So occurrence, if you see, of dioxygen, about 1/5 of the atmosphere is free of elemental oxygen. Here if you see that O2 comprises of how much percentage? Approximately 21% of the atmosphere, right? In the combined state, if you say, that means in the form of water, it is present as 89% by weight in Earth's crust, and about 50% in Earth's crust. Plants and animal tissues, it is 50 to 70%, right? So in the atmosphere, if you see, pure O2 will be present in as 21%, right? And in the form of water, it will be 89% by weight. In Earth's crust, it is about 50%, and in plants and animal tissues, it is about 50 to 70%. Structure, if you see, if we draw the MO diagram of basically O2, that means how many? 16 electrons are there, right? 8 each. So this will be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2p2, pi 2px2, pi 2py2, pi star 2px1, pi star 2py. So here if you see, it is paramagnetic in nature, and if you calculate the bond order, it will come out to be 2. That means it is present at O double bond O. Isotopes, if you consider, O16, O17, O18. So maximum amount of oxygen is present basically in 16, while 17 and 18, if you see, the ratio is 1:8. Coming on to the laboratory method of preparation. So what is the first preparatory sorry, what is the first preparatory method? By heating oxygen containing salts. For example, let us take chlorates, nitrates or permanganate salt, and when you heat it, you will get oxygen as the product. So this important reaction you have to remember. KClO3 on heating with MnO2, basically it is acting as a catalyst, right? It will give you KCl plus O2. So this is how in laboratory we prepare dioxygen. By the thermal decomposition of the oxides, which are lower in the electrochemical series, means they are unreactive basically. For example, if you say silver, mercury, right, their oxides, if you heat, they will produce oxygen. Here also lead, if you see, their oxides, if you heat, they will produce oxygen. So this is a type of a thermal decomposition because we are providing heat basically, right? Hydrogen peroxide, if you decompose it basically, right, it will give you H2O plus O2. This is the another method for the preparation of dioxygen gas. So these reactions you can write down. Now we will move on to the next. See, on large scale it can be prepared from water or air. You must have done it in class 10th, right? The first chapter, right? Electrolytic decomposition basically. So there was electrolysis of water, if you take, right? One acts as cathode and one acts as anode. So in electrolysis, if you see, anode is positively charged and cathode is negatively charged. If you take water as the electrolyte basically and pass electricity, so hydrogen will be produced at cathode and oxygen will be produced at anode, right? I hope we have done electrochemistry, so this will be much familiar to you, that H plus on reduction will give you basically hydrogen gas, right? and water on oxidation will give you O2 gas, right. This occurs on anode and this occurs on cathode. Industrially, if you see fractional distillation of air, right. If you see that air, if we take and we remove carbon dioxide from it and water vapor, then the remaining gases will be what? Basically the nitrogen and the dioxygen, right. So here if you see that boiling point of oxygen is high, right. So when you heat to a particular temperature, the nitrogen gets boiled off and you are remained with the oxygen itself, because the boiling point of oxygen is higher than that of the nitrogen. So this is the a basic method of fractional distillation. Next, if you see, dioxygen is a colorless and a odorless gas. Its solubility in water is to the extent of 3.08 centimeter cube in 100 centimeter cube water. That means 100 centimeter cube water you take, it can dissolve particularly 3.08 centimeter cube of oxygen at 293 Kelvin, right. Means at room temperature this much amount is soluble in 100 cm cube of water, which is enough sufficient for the support of the marine and aquatic life, right. So because of the greater solubility, if you say that in water oxygen is soluble, so to some extent, not to a greater extent, but to some extent, that is why the marine or the aquatic life can breathe under the water, right. So it liquefies at 90 Kelvin and the freezing point of dioxygen is basically 55 Kelvin. Now dioxygen, if you see, it reacts directly with nearly all metals and non-metals, but if you consider the inert metals, right, such as gold, platinum or some noble gases, if you see, direct combination is not possible because they are inert in nature, right. Now the combination is highly exothermic. The combination is highly exothermic, that means it releases heat, and we know where there is a bond formation, generally the heat is released, right. Now it is very important that however to initiate the reaction, some external heating is required. Why? Because if you consider O double bond O, it is having a high bond dissociation energy. That is why for the direct combination of a particular, let us say metal plus oxygen, first you need to supply heat to that particular reaction so that this bond gets broken up, and then it will combine and release heat, and therefore known as an exothermic reaction. So this is the direct combination, C plus O2 giving CO2, P4 plus 5O2 will give you P2O5, S plus O2 is giving you SO2, N2 plus O2 is giving you 2NO, Mg plus O2 is giving you MgO, magnesium oxide, Na plus O2 is giving you Na2O first, and then it is coming on to Na2O2, that is basically sodium peroxide, O2 2 minus. Pb plus O2 will give you PbO2, Fe plus O2 will give you Fe34, which we have studied, it is mixed oxide, right, of FeO and Fe2O3. So these are the examples that how particularly dioxygen combines with non-metals and metals to give oxides, the corresponding oxides. Now, here if you see, combination with O2 is accelerated by using a catalyst, right. So in some reactions we use particular catalyst. For example, H2 plus O2, we use the platinum as the catalyst. Ammonia and oxygen forming NO plus 6H2. These processes you have to remember by name. These are important. These processes you have to remember by name, especially Oswald's contact and Duyken's process. So SO2 plus O2 in the presence of B2O5, these we have done so many times that it yields SO3. So this is basically a contact process in which SO3 is being formed, and the catalyst which is used is vanadium pentaoxide, right. Here if you see HCl plus O2, if you use copper chloride, it will lead to the formation of H2O, that is oxide of hydrogen basically. So it is known as the Duyken's process, in which the catalyst is copper chloride. You can write down these processes. Along with the catalyst. Now next question is, it is possible to obtain oxygen from air by fractional distillation because oxygen is in a different group of the periodic table than that from nitrogen. Oxygen is more reactive than nitrogen. Oxygen has higher boiling point than that of nitrogen, or oxygen has a lower density than that of nitrogen. What should be the answer for this particular question? What should be the answer for this particular question? We have already discussed this. Sham is saying D. Okay. What about others? Look at the options carefully. I have discussed the answer in the previous slides. I have specifically mentioned the reason. Anyone else with the answer? Amongst A, B, C, D, which one should be the answer? Shivani, Shivranjani, anyone with the answer? Arun, Maria, Tasneem, Shraddha, Arvind. Yeah, Sham. Now you are correct that the answer is C. Oxygen has higher boiling point than that of nitrogen, and therefore the oxygen remains in the vessel itself while the nitrogen boils off, right? So we are able to obtain oxygen from air by fractional distillation because oxygen has higher boiling point than that of nitrogen. Good. Now the next question says that on heating KClO3 we get, on heating KClO3 we get which of the products, A, B, C or D? This also I marked important. This answer you should know, we have discussed in this session only. Perchlorate basically on thermal decomposition yields what? Okay, Sham is saying B. Anyone else with the answer? Anyone else? What about Shivranjani, Shivani, Shashank, Tasneem, Tara, Arvind? What are your answers? So the answer for this particular question is B, that is KClO3 on thermal decomposition will give you KCl plus O2. So Sham, you are very much correct with the answer. Good. Right. Next question. KO2 is used in oxygen cylinders in space and submarines because amongst A, B, C and D, which one should be the answer? Yes, Shivranjani, you are also correct. Potassium superoxide is used in oxygen cylinders in space and submarines because, what should be the answer for this particular question? You can apply just some common sense to this particular question also, that what is lacking in space and submarines, that why potassium superoxide should be used in oxygen cylinders. Sham is saying A. Okay. What about others? So here if you see, KO2 combines with CO2 to give K2CO3 plus oxygen. So this is the method by which we can prepare dioxygen, right? So potassium superoxide is added in oxygen cylinders in space and submarines because it absorbs CO2, leads to the formation of K2CO3 and produces O2. That means it increases the oxygen content in the oxygen cylinders, right? So for easy breathing basically. Now uses of dioxygen are, it is used for breathing, in welding and cutting. If you see oxyhydrogen or oxyacetylene torch is used. In iron and steel industry to increase the content of blast in the Bessemer and open hearth process. Right, these processes you can study. Basically you can write it down. In iron and steel industries it is used. Now the fourth one is, it is used as a fuel in rockets. This is important. This is the important use of dioxygen for breathing and as a fuel in rockets. You can remember these both. Okay. Chemical properties, if you see, with NO it gives reddish brown fumes of NO2. We already know that color of NO2 is what, basically reddish brown. So NO plus O2 will give you NO2. Absorbed by alkaline pyrogallol. So what is pyrogallol basically? 1, 2, 3, 4, 5, 6. So 1, 2, 6 hydroxybenzene is known as basically the pyrogallol, right? So oxygen is absorbed by this particular thing. A smoldering wood splinter burst into flames in a jar of oxygen. So basically what is done here, that combustion is done in pure oxygen. In pure oxygen we do combustion of wood basically, right? So it burst into flames. So these are the tests which are done by oxygen basically. Now, yeah, so that's all for today. So we have done the basically halides. Oxides are also done of the 16th group, and we have elaborated the uses, the properties of dioxygen, right? So that's all for today. Happy learning to all.